Good evening, good afternoon, everyone. Welcome to the session number 4 of KSS conference. This session is titled Efficient Memory Systems. We have the first paper on this session, which is also a best paper candidate. The paper would be presented by Professor John Jose. Professor John Jose is an associate professor with the Department of Computer Science and Engineering, IIT Indian Institute of Technology, Guwahati. He completed his PhD from IIT Madras in 2015. He is also the recipient of prestigious Qualcomm Faculty Award in 2021. He currently serves as Vice Chair of IEEE India Council. His research explores around domain of NOC, cache management techniques, and multi-core systems, non-volatile memories. He is also associate editor of the IEEE Embedded Systems Letter. I welcome Professor John Jose to present the paper titled ZPP, a dynamic technique to eliminate cache pollution in NOC-based MPSOCs.
Thank you, Professor Venkatesh, for the introduction. Good afternoon, all of you. I welcome you to the paper, JPP, a dynamic technique to eliminate cache pollution in NOC-based MPSOCs. The authors are Dr. Deepika Der. She was my PhD student. Now she is working in Intel. Unfortunately, she could not travel. She couldn't get a visa. So I'll be presenting on behalf of her. So this is going to be the outline of my talk. Since considering the heterogeneous background of the audience, I'll take up 1 minute to introduce about tiled chip multi-core processors. And then I'll talk about the concept of what is prefetching. And then the work that we are talking about, JPP, what is the motivation for that and its working principle, and then briefly touch upon the experimental results and analysis. And then over the poster session, we can have detailed discussion also if the time permits. So as we all know, whatever kind of future applications that we are talking about, be data centers, autonomous cars, mobile phones, smart homes, wherever it is, multiple processors are working together. We are in the era of multi-core processors already. A specific category of multi-core processors have been known as tiled chip multi-core processors, where we can see that this is a single chip which has multiple tiles on it. You can see that they have been organized as row-wise and column-wise, just like how you see the tile architectures. And the memory controllers are typically connected to the corners. So if you have, let's say, a memory that has been connected through 4 channels, then they will enter into the chip just like different gates into a stadium. The data is going to enter into the chip through different points. They are the memory controllers. And then the diagram shows a 64-core tiled chip multi-core architecture. And then we are organizing the tiles as 8 rows and 8 columns. So we call it as 8x8, 2-dimensional mesh topology. Now, if you look into what is there inside a tile basically consists of a core, which is generally your processing engine, your out-of-order superscalar processor, with a private L1 cache, which is very specific to this core, and a shared distributed L2 cache. Just to introduce what do you mean by shared distributed L2 cache, imagine you have a textbook consisting of 64 chapters, and then if it is very costly, 64 friends plan to keep one chapter each one of them. So it's just like one textbook, but they are physically scattered across different tiles. So in short, here you have 64 tiles. So your part of the L2 is being kept in various tiles. So rather than your L2 keeping it in one place, then centralized place, it is now scattered, but it is shared. And then these tiles are being interconnected by packet switching based network on chip, which is the common communication infrastructure used in multi-core processors. Now imagine that, let's say you wanted to execute an instruction that is being shown in this particular gray tile. So typically it fetches from your L1 cache. If it happens to be a miss, then naturally you have to go to the L2 cache. Since your L2 cache is not in one place, few of the bits in the physical address will tell you which tile the corresponding L2 maps. Then in this case, for example, we can imagine that few bits will tell you that this is going to be the L2 tile. We call it as the home bank of the address. So then in order to fetch the L1 cache missed block, a packet has to move, or the data has to move from the request has to move from here all the way to there. So in the technique of network on chip, we generate a request packet, which will travel from this particular tile through XY routing. It travels along the X dimension first, followed by a 90-degree turn, and then moves to the Y direction. The request packet will travel through the network on chip, and then you perform a hit or miss check in the corresponding L2 tile. And if you are able to find the corresponding block, then reply the data, and then that also will travel in an XY routing manner all the way back into the source time. But it can be potentially L2 cache miss as well. So in that case, you need to go to the next level, that is the main memory. So that also will travel through the network on chip depending upon the address bits, which will tell you where the address mapping is. It can be either to MC1, MC2, 3 or 4, what the case may be. So an L1 to L2 traffic travels through the NOC, and L2 to the main memory controller, both the request as well as the reply travel through the network on chip. So the traditionally Unicore system, when you talk about a cache miss or a L1 miss penalty, it's a fixed quantity of time. You go to L2 and bring it back. Here, depending upon where is the corresponding L2 bank, then your miss penalty also will vary. Sometimes if the miss is going to be in a nearby tile, it may be very few cycles. If it is in a far off tile, it's going to be larger. This is called non-uniform memory access, which is a common terminology that is being known. So in short, L2 to main memory controller communication also happens through the network on chip. Now let me try to introduce what is the concept of prefetching. Prefetching is a very old concept used in the architecture community to bring something a priori before it is being required. So prefetching technique that fetches a cache block ahead of time. So we are going to talk about a scenario. Let's say we have a main memory which consists of a few blocks as has been shown, and take up a simple cache with a set 0 and set 1. So imagine the numbers, the alphabet that is shown is there, the data. So currently we have set 0 and set 1 holding some data P and D that is already been there. So imagine there is a cache miss request that is going to happen at this block. So you are going to bring B. There is a requirement to bring B. So you go to main memory, go to the block B. If there is no prefetching, then only B will come. But in the case if prefetching is enabled, you find out one more block or two more blocks as the case may be, depending on the aggressiveness that you prefetch. So along with you, you carry one more block. That's the case what you are going to see. You are going to replace your P and D what you have. In this previous case, you have P and D. Now this P would be replaced with D, that is the demanded block. And the D, which is the adjacent block, is replaced with C. So your D is being replaced with the C. So B, we call it as the demand block, and the C is the prefetched block. Now the trouble is there are some pros and cons for prefetching. So what happens is if you have a core without any prefetching, it's fine, your C won't be coming. But if you're having a prefetch engine, then you have to predict what to prefetch, how much to prefetch, and then take a call where to keep the prefetch blocks. So in this case, like you can see that a typical cache memory block that you see, it has few fields which will tell about whether the cache block is valid or not, whether it's dirty or not, in order to represent whether it has been returned. And then you have the tag bits, that the standard one. And then when you work in a coherence enabled system, then the cache block need to have various states associated with that. So state value is stored, and for replacement we use few LRU bits, and then comes your actual data that is being stored. So in a prefetch enabled system, there is one more bit that will tell you whether the block that you are talking, is it a demand block or a prefetch block. So cache contains the demand block as well as the prefetch block. So when you prefetch, what happens? You are supposed to reduce the cache miss, a potentially future request. You are telling that I am able to predict that this particular miss will happen, then I am keeping it early. So it will reduce cache misses. Then you will be able to reduce the tile communication at that point of time, because if it is two separate misses, then one you send a request and come back. If you prefetch with one request, you are getting two replies together. So that will reduce little bit of your traffic in the NOC. So overall network stall time would be reduced. Now what is called cache pollution? So look at this case, I am going to put your C, which is a prefetch block. Now C has replaced something, let's say D. Now immediately whatever you have thrown out, if that is being required, this prefetched guy actually polluted my cache. I was kept everything safe and secure, fine. But because of my over enthusiasm, I put somebody there and he evicted someone that is really required in the near future. So before C is being demanded, I wanted that block which has been evicted out. This is called cache pollution. So sometimes if the prefetching is not correct or not accurate, and sometimes the block that is been evicted out was a most recently used block, then sometimes prefetching can create cache pollution. So prefetch evicts block, which is importantly or frequently used in cache block. This is a problem associated with any good prefetching technique that you talk about, because you are evicting a block in order to get advantage in the future. So when you talk about any kind of prefetching techniques, the most important parameters that you work on, either one thing is going to be the accuracy of the prefetcher, sometimes the timeliness. We brought something, but then before he has been thrown out, are we using it? That's called the timeliness of the prefetching. And the last one is coverage. Before something missed, are we able to keep that block in time? Now moving further, So when you work in a multi-threaded environment where multiple threads are going to share a data, and managing of the shared data often requires cache coherence protocols. So for consistency across caches, shared caches use cache coherence protocol, and one of the classic coherence protocol is known as MESI, where M stands for modified, E for exclusive, S for shared, and I for invalid. So every cache block is been categorized into one of these four, depending upon what kind of use the processor has on this block. So then we need to store the state of the cache block also here. Now in MESI protocol, the value of the state fields are M, E, S, and I that I already mentioned. Now there is something very specific. E and M means, E means this block is exclusively kept only by one L1 cache. So that has the value. It's only for a reading purpose. But M means somebody has kept the block in a modified state. So now you consider two levels of cache, and typically we go for an inclusive cache, an L2 and an L1. L1 is, if L1, L2 hierarchy is inclusive, means it's a copy paste from L2 to L1. Once you do copy paste, then this block, what is kept in L1, the processor uses it. Now, if that is in a modified state, the processor is free enough to make changes in the block because it has modified writes. Nobody else keeps the copy, only that particular processor keeps the copy of it. Now, when you make changes, what happens to this block in the L2? The L2 tells that it is in the modified state. Some other private processor L1 cache has it. So this is a stale data, because the latest value is available somewhere. We try to target upon that, the stale data. So E and M, these two blocks, they indicate that L1 cache exclusively owns the block. So the modified blocks in the last level cache or in the L2 cache in this case is in a stale state. So updated cache block is stored in some private cache level. So modified blocks, so now it is like you have two levels, and whatever value that you have in your L2 cache, it's not correct. The L1 cache is correct. So it's, you are keeping two blocks more or the same data, only few bits or few byte values changes. Can I try to exploit this, which nobody is going to use? The moment it is modified state, only the processor that keeps the L1 private copy will going to access it. Anybody wants it, that is going to supply the data in the case of an MESI protocol. Now let's see something about prefetching, what happens. This is a diagram which shows a tile in which you have the L1 cache, where the blue color indicates these are the prefetched blocks and the red color indicates these are the demand blocks. This is the way how a conventional prefetching works. You, along with the demand blocks, you bring the prefetched blocks as well. Now, if you look at the L2 cache, in the L2 cache, a copy of this is being kept here. Now, if you look at the copy, some of them are in exclusive state. For example, if this green color block indicates a copy of that is residing here, but that is in the modified state, that means processor can write on it anytime. So that copy and this one are not coherent, not the same value. So whatever you keep here, if it is a modified block, its data is not to be used, it's not correct, only this one is correct, and that processor will make use of it. So if you look at this, your L2 cache, so in this case, you just see that you have this prefetch queue, depending on address, you are going to bring the block into the cache. It can be demand blocks that is there, or it can be prefetch blocks as well. And then your L2 caches will hold the value. Now, if you go for a tiled chip multi-core architectures, this is not your L2. Your L2 may be mapped to maybe tile number 9. This is that L2 blocks which are currently residing in tile number 3. Depending on the address bits, your blocks may not be in the same tile. It can be in different tile as well. Now, let me try to talk to you about the experimental framework that you used, and then I come to the motivation. We worked in the Jump 5 simulator, and we modeled a 64-core tiled chip multi-core architecture. These are the parameters with L1 and L2 caches. Typically, it's a standard value that has been used in the MESI cache coherence protocol, and the access time that has been taken. And we made use of PARSEC and the spec standard benchmarks to evaluate the performance of our technique. Now, the question is, do existing prefetchers causes pollution? What you see on the x-axis are standard prefetchers, the state-of-the-art prefetchers that you have. So what it tells is, all of them, so for example, if you take the very first one, this particular technique, it has roughly 25% of your blocks are suffering from cache pollution. That means the block which has been evicted out and you have kept the prefetched block, that was reused. So had that prefetching not happened, we could have used it again. But it is, here I'm talking only about the pollution, but all of these prefetchers have very good performances. I'm just talking about the pollution aspect alone. So So all the state-of-the-art techniques, they have some level of pollution that has been happening because the root principle by which we work is you evict a block and then you keep the prefetch block. Now, can you rethink in a different way? Now, the second question is, what is the percentage of stale blocks? Like what I mentioned, if you have a modified block in the private L1 cache and your L2 cache, wherein you are going to keep it, is it stale? What is the percentage of that? And the next question is, how frequently prefetch request is being generated? So our study shows that this is the first one. We worked upon one benchmark called VIPS, WIPS, the parsec suite. And during the simulation, the x-axis shows the simulation from 1 million over to 100 million. The green bar shows that what is the percentage of the blocks in the last level cache, they are stale. Stale means these blocks have a private copy that is in the modified state. As we can see that over the time, the percentage of stale blocks keep on varying. Sometimes it can come to very low value. Sometimes it can go up the ladder also. And we tried with the single-threaded multi-programmed workloads in spec also. I'm just taking only one of the benchmark for you to understand that more or less the numbers will vary across. Now, what is the second graph? So the green graph shows that, or the green line shows that over the simulations or over the execution window, we can see that the percentage of stale blocks vary. Now, the red bar shows, the red chart shows that what is the number of prefetch requests. The number of prefetch requests also, we can see that there is plenty of prefetch requests that is been there, and that also keep on varying depending upon the misses that happens. Now, the question is, if you have stale blocks, can I keep your prefetched block in the available state blocks? So this will work very well whenever the red bar is lower than the green bar. But we have certain scenario where you can see that here the red bar is more. So the number of prefetch block is much more than the number of stale blocks that has been available. So now we are proposing a technique known as zero pollution prefetcher. It's known as JPP. So what is JPP? It's an intelligent caching of prefetch block. I'm not going to propose any new prefetching. State-of-art prefetching technique is being used, but where I keep the prefetch block, that's where we work on. Second one is what type of prefetcher that CPP uses. It is an L1 data prefetcher. It's trained with the L1 cache miss. And where does CPP places the prefetch block? In modified locations of the last level cache of the source type. So consider the case that you are generating a request from this. It's a miss in the L1 cache. And this is the home bank. You go travel through the NOC and bring it. This is the L2 cache corresponding to the same physical address. You come and see in this type, do you have any stale block or not? If that's the case, you put your prefetch block there. Don't put your prefetch block on the L1 cache. You put it in the L2 slice of the same type. So now whenever there is an L1 cache miss, don't go here. You are not going to have any kind of pollution because you don't touch your L1 cache. You try to make use of here. So it is slightly more than an L1 hit, but it is much, much lower than an L2 hit because you are going to place it in a same type. So we are going to keep the blocks in the modified locations of the last level LLC source types. So what are the benefits? It eliminates cache pollution. I'm not going to replace anyone. So I'm not going to have any kind of pollution that will reduce further cache misses. Utilizes the last level cache efficiently as the modified location contains the stale data. Why do you keep it? Can I make use of it? So essentially what I do is it reduces network packets generated due to cache pollution. And then in short, what we are trying to do, rather than expanding your L1, typically any kind of prefetching technique works by having some extra buffer or trying to replace some of the blocks. So don't try to expand your L1. The L1 is as it is. Try to find out places in the L2 tile where the data is no longer meaningful there. So try to make use of that and keep necessary bookkeeping mechanism such that this coordination can be seamlessly done. So what is the working principle of CPP? So prefetch blocks upon reaching the requesting tile, it searches and find out the stale modified locations in last level cache and it places prefetch block in the stale location. So this is your L1 cache and then you can show from the color coding, the green one are the exclusive blocks. So that means its copy is present in the L1 cache, but then this value is no longer being required. Now to perform the bookkeeping, how do you coordinate that? We have a small hardware module which is known as a tracker. So tracker is an additional hardware which will use to store the tags of the prefetch block. Now think of a case that you have a prefetch block that has been coming and you know that it's a cache memory block. It has a tag portion and data portion. What I do, the data portion I put it here. I don't disturb the tag portion of the already existing one because that is required for coordination between L1 and L2. And then the tag of this I am going to put up in the tracker. So what you have, the tag will go there and the data will come over here. And whenever there is a request that is going to come, so first you parallelly search in the L1 cache as well as in the tracker. The moment you know it's a hit, that means this particular block is available in the stale location. So you need to find out how do you get it, from which stale location I'm going to get it. So then accordingly, once if it is a hit in the tracker, that means the data is already present here. From there, you promote the data and then you get. So it is slightly more than a typical L1 hit, but it is much, much lower than a typical L2 hit. So that's the advantage that you get without expanding your L1, without any cache pollution. So how do you work with it? What is the logistics behind this? You have a prefetch block mapping is required. You have a tracker that is been doing, and then you need to have a mechanism by which you place the block, and then how do you invalidate? Because whenever there is a write back that happens, how are you going to manage that? So quickly going through, if you look at the addresses of an L1 cache and L2 cache, it basically works with the same address. And if you see that the typical size of L2 is bigger, so these are the bits which you need to be careful. For example, if I'm talking about a request which got a hit in set number 5 in L1, for example, if it's a miss in L1, then when you go to L2, then this is the set number in which I have to go. So when I am bringing something and keeping it in L2 cache, I cannot simply keep it wherever I want. It has to be kept in very specific location, only in these sets. For example, if the value is 5 here, I can keep it set number 5, I can keep it set number 37, I can keep it set number 69, like that. So conventional block mapping in L1 and L2 is a motivation behind its performance. So wherever you are going to keep, it's based upon a very limited set. You are not going to keep it anywhere. And the maximum location that can be used by JPP to place prefetch block is equal to the number of mapping that you get. In this case, you have 8 mappings into the number of L2 ways. So to reduce search space, you can use few more bits, which will help us the easy searching of that. Now, if you look at the tracker, what it does, the tracker also need to have some kind of bit field. It's a valid bit is there, which will tell you whether the entry in the tracker is there, and it will store what is the set number and what is the way in the L2 that this particular block is there, and the tag is also that is been kept there. Whenever tracker is full, the MRU bits will tell you what is eviction mechanism inside tracker. So these are the number of bits required per block inside. So typically it requires 5 bytes of data. So I'm not storing the entire data. My data is kept here, and my tag and other information is kept here. So parallel searching, it will give you the performance. And where am I going to place it? First, when I bring a block, I need to look into the space whether I have an entry which is stale. If stale, then using tracker, I put up the data, and accordingly the bookkeeping is been mentioned. The details of the bookkeeping mechanism and controlling, it's kept in the paper or free enough to come and talk to us. In the interest of time, this correlation mechanism I'm not talking here. I'm mostly talking about what is the concept that is being used so that we can achieve it without pollution. Now, the last and important point. How do you, whenever there is a state change, it's in a modified state, it is not going to be modified permanently. It can become M2E, so it can become M2S or M2I. So whenever this transition happens in L1, what do I do? Because that particular block in L2 is been kept by someone else. So at that time, I need to replace them. So there are 3 ways in which we do. So the first way is known as CPP with no reordering. The moment the state change happens, the extra guy will be thrown out. The second one, I come to know that this particular the write back is going to happen or the state change. So I search for some other space in the available set. That is called reordering. And the third one is known as a kind of a controlled reordering. All those blocks which are brought from the nearby tiles, I throw them out. But those who have come far off places, I give them preference. So these are the 3 ways in which work. And then just to conclude with the results, 3 more slides. So what we are showing is the number of hits that we observed. The green one is the normal hits that a cache has for various workloads that we have taken. This W series is the workloads from spec, and these are from parsec. The yellow color is the extra hits, the percentage of hits that we got from the CPP expansion. Across workloads, you can see that CPP is going to get the benefit. And then the next aspect what we worked on it is about the useless packets. So we are bringing and the packets are being used because it's kept for a longer time than eviction out. So the lower the bar better. So useless packets are significantly reduced. These 3 variants is being shown here. And BOP is the best state-of-art prefetcher. We are comparing with that. And this is, we are able to reduce the number of cache misses also across all workloads because we are not throwing out. There is no cache pollution. So because of that, we are able to improve cache hits. And this is about accuracy. Across various benchmarks, we are able to improve accuracy. We are able to improve the coverage as well. because the pollution is being brought to zero. And the last one is, we were just trying to see how many of them are working in the zero version. That means without reordering, and this is with reordering. So we see that for different benchmarks, sometimes it works in the reorder pattern, sometimes it works with the no reorder pattern, just trying to see how adaptive the system is. So to conclude, before that the overhead is, we are able to reduce cache misses up to 62%, and the network stall time is reduced because we have significant amount of cache hits without any extra spaces. Weighted speed up is going up as high as 2.19, and average memory access time is reduced. And of course, since there are extra modules that is being kept, there is slight area and energy overhead that is been coming over here. And so the conclusion is CPP utilizes the redundant location in LLCs for prefetch block placement, completely eliminate cache pollution. And here is one of the drawback of our technique. If application where majority of the blocks are in shared state, not into M state, most of them reading happens, then we don't have enough number of stale blocks. So in those cases of application, GPP may not be the right choice. CPP can be a cost-effective design choice for cache prefetch block placement. Thank you for that.
We have time for questions.
For the presentation. Couple of questions. So let's say the interconnection technology is not a network on chip, but it's a bus-based architecture. Would the technique change significantly? That was one question. And secondly, the other question was, if we have another level of cache, let's say an L3 cache, what do you suggest? We would place blocks in L2, still in L2, or maybe we will place blocks in L3?
Thank you for the question. To answer the first one, this technique will work on every architecture where you have a shared distributed last level cache, whether it's L2 or L3, wherever it's shared distributed. So you have some slice of last level cache, part of the same type, you keep it there. So you keep it somewhere in your home rather than keeping it far. So wherever be the scaling or topology, it will work.
So basically, what I was wondering is that you can bring more prepaid block in the last level cache instead of basically keeping L1 without. So I'm just wondering if that gives you the.
The one that we are doing, if I understood your question correctly, we are not keeping anything in L1. We are keeping it in the last level cache slice of the same type with the requesting one. So I'm not replacing L1, I'm just keeping it in the nearby place.
That's in L2.
In the L2 of, this is not your L2. It is the L2 of that tile, which happen to have some stale blocks. So from your home L2, you bring it to the local L2.
I have a preface buffer.
Yes.
Separate buffer for preface. Does this technique work there?
No, if I have a prefetch buffer, then you have to take a call whether you will keep it in the stale L2 or in the buffer or the access time. So if it's a small buffer, then the access time may be easy. How do you access into the buffer? Here it is like you have space. Since the bigger the space, the indexing into the L2 cache will take slightly more time. So the advantage you get is storage versus access time, one cycle more. So we can use combination of this. There can be a case there's potentially, what if there is no stale block? That can be the case. Then you are not going to keep and prefetch it. Then a buffer will.
John, you said is a NOC and all these things. So what is the role of communication? What's the scalability? Where do I have to place these memory controllers? Have you looked into this?
The memory control.
Yeah, because you showed a 2D mesh.
Yes.
Why do I need a mesh?
It need not be mesh.
Yeah.
Whatever be the
So
architecture.
have you guys quantified the role of the NOC? Because I saw all, N1 computer architecture. How does communication function? And what is the contribution of that when you are
Okay. So when you have the number of hopes that is going to increase, if it's like a large network, the overhead of prefetching that you do is more. So when you go for a 3D structure or a different kind of a topology, the amount of the effort that I put in prefetch something is more. So if I can carefully manage, my effort is fruitful. So it will scale up to any topology. It's the trade-off that I do with the effort that I put in. So we have tried with 8x8 mesh, and for smaller tiles like 4x4, it's not giving much of the performance because even if it is a miss, I can go and quickly bring it. This really makes sense when the NOC latency or the number of hopes, the potential hopes is much larger. Yes. Yes.
Okay, thank you. We'll running short of time, so maybe we can discuss after that during the poster session. So we'll proceed with the next paper. The next speaker is Xiu Li, is a PhD candidate from Duke Center for Computational and Evolutionary Intelligence. It's advised by Professor Iran Shen. His research interests include computer architecture, software, hardware, co-design for deep learning systems, and near data processing. The paper is titled EMSI, an efficient memory system design with specialized caching mechanism for recommendation inference.
Thank you for this introduction. So I'm Shuli from Duke University, and today I'm going to present our work called EMSI, an efficient memory system design with specialized caching mechanism for recommendation inference. So this is a collaboration between Duke University and Samsung Semiconductor Incorporation. This is the outline of my presentation. So first, I will give the introduction of the background and motivation of this research, and then introduce our characteristic study showing that there's a potential for acceleration of this memory system design, and then present our design of the EMSI system, and finally present the evaluation result of this design. So first, recommendation model is quite popular today that apply on a kinds of different applications, including video recommendation, the ads click-through rate predictions, the search engine, and the e-commerce. And it consists of a huge portion of the workload that actually running on the data center. And one of the most popular used model for recommendation system is called the deep learning based recommendation model, or DLRM. So on this figure, we show the architecture of those recommendation models. So we have dense features and sparse features, where for the sparse feature, we use a one-hot or multi-hot vector represent the categorical features of the inputs. And during the inference, we use a operation called embedding lookup to convert those sparse features into a dense feature so that we can perform the interaction between those input features, and then use a MLP or multi-level perceptual model to generate the final prediction of this model. So during this embedding operation, we have a embedding table, and we use those inputs as index to perform the embedding lookup. Basically, we find all the corresponding vectors, we sum them up together to generate the embedding result. So this operation, sometimes also called sparse length sum, is actually a element-wise sum. So there's also other operator that can be applied, but that is diagonal to our design this time. And typically those tables and vectors consume up to hundreds of gigabytes. So that is the major challenge of design such kind of system. Appraisal work perform a performance analysis of such kind of system as shown on these figures. And we find that the sparse length sum actually dominates the overall latency. And because it is, the embedding table lookup is actually a memory intensive operation, and it also requires a lot of irregular and sparse memory access, which is relatively hard to optimize. And there are previous solutions that trying to address such kind of issues. One of issue with the near memory or near storage computing. So there's one such work called AXDIM, which designed a specialized DRAM-based near memory solution. But such kind of design, although it provides a significant speed up, but it requires significant internal hardware change. It requires some additional digital logic near the DRAM bank, which increase the manufacture cost, and you have to specialize the chip for your purpose, which could be very expensive. Another type of design was based on near storage computing solution, where build some computing logic in the controller of the SSD devices. But such kind of device, because of the power budget and the overall design budget of SSD showing limited parallelism, and also limits its own computing power. We all see that this such kind of solution showing a relatively high research and development cost, because you basically need to redesign the whole memory or SSD devices. And those designs showing a relatively simple cache mechanism, And another type of design that's utilizing the production system is a software managed cache. But because it's a software managed one, it shows a relatively long latency to execute the policy and actually communicate the data across different devices. That brings our motivation of bringing a new memory system design. So we want to base those design on existing products with minimal changes and introduce low research and development costs. And most importantly, we want to reduce the overall memory cost. So this solution can be relatively cheap. And we want to utilize the rich on-chip memory resources, especially on FPGA and other devices for caching. And we want to build those cache in a hardware managed base and use the prefetch policy to reduce the data movement overhead. And so it comes to our selection that we use the near data processing solution to build such kind of system. So our platform, we select the Compute Express Link, which a coherent interconnect standard that will be used in the next gen system and combined with a FPGA and SSD. So the SSD is used as expanding the overall memory space of the system, while FPGA provides the computing power for support those kind of applications. And the CXL provides the possibility to perform point-to-point communication between those two parts. And a little bit more background on the Compute Express Link. So this coherent interconnect standard provides the possibility to give you a unified memory space of the system. So the memory on the device can be mapped as a host managed device memory or HDM, and you can access it either from the host CPU or your own devices through the unified host memory physical address space. So there are 3 protocols provided by the standard and 3 types of devices defined in the standard. Type 1, 2, 3 as for the peering cache, the accelerator, and the memory expander. So the latest standard CXL 3.0 also provides the CXL switch that support the point-to-point communication. So before jumping into our own solution, we want to first present the characteristic study to show the potential of acceleration of our proposed solution. So we compare the solution that use only the SSD or use only DRAM or the combination of SSD and DRAM for storing the embedding vector and support the inference system. And our conclusion is that the platform with the combination of the SSD and DRAM is the optimal choice to achieve the balance between the cost and performance. So although DRAM is fast, but the cost of using DRAM, buying a lot of DRAM is quite expensive. Well, although SSD is relatively cheap, but it is slow. So combine those two will give you a better solution. And we also find during design system, the several parameters of your caching, of your cache structure need to be carefully figured. So we studied that adjusting the associativity and the cache capacity. We found that in our target workload, adjusting the associativity does not show significantly improve the cache hit rate, while the cache capacity is the critical factor that affects the performance of this memory system. Another thing to consider is the granularity of the cache, or how we replace, what granularity we replace the data in the cache. So we select 2 candidates. So one is at the vector size, which the granularity is the size of a embedding vector, and also another one is the block size. So it's size of page in the NAND flash. And we find that for different workloads, so different granularity, the different granularity will be the optimal. So that means we need to select those replacement granularity based on our workload, or the replacement policy have to be a workload aware one. With those in mind, I will bring our design of the EMSI. So this is the overall architecture of our system. We have a SSD, which is modeled as Type 3 devices or a memory expander, used to store the hundreds or even terabytes of hundreds of gigabytes or even terabytes of the embedding vectors. We have an FPGA, which modeled as a Type 2 devices and used as a major computing devices that perform the inference and also buffer those embedding vectors. We also have a CXL switch that supports the communication between those two parts. And this is our structure of our memory system. So we map the SSD and HBM or the memory on the FPGA as a host managed device memory. And we also have 3 levels of cache. So the level 1 is the on-chip memory blocks of the FPGA, and the level 2 is the HBM on the FPGA, and the last level is the internal DRAM of the SSD. So we need to have some modification over a simple cache design. So first thing to consider is where to store those tags. So because we have a quite large L2 cache, which is 16 gigabytes, so it's not like the conventional L2 cache in the CPU system, but is a cache that's in the memory system. So the tag will be quite huge, and we need to find a place to efficiently store and access them. So we select the on-chip ERAM, which have a relatively narrower interface, but a more capacity on the FPGA, and we use ERAM to store tags. And we find that the memory consumption of tag actually depends on the overall memory space, the cache associativity, the cache block size, and also the overall size of the cache. So the memory space and the cache size that we cannot change because it's defined by the system itself, but we can select the associativity and cache block size. So if we increase those 2 factors, we will reduce the overall memory consumption of our tag. So we also have some constraint here. So we need to support 16 gigabytes of L2 cache, and we also only have limited on-chip memory available for the tag storage. So based on this, we select the 4 kilobyte block size and 8-way associative for this memory, for the L2 memory, so that we can we only require 8 megabytes of tag, which can be stored on the on-chip ERAM of the FPGA. And we also have a customized replacement policy, because one of the most important and interesting feature in the recommendation model is that the access pattern of the embedding vector shows a power law, which means a small amount of vector will be frequently accessed, while the other embedding vectors are rarely accessed. So we can utilize those characteristics to tailor our replacement policy. So our solution is that we sample some queries from the data set, and we calculate the number of most frequent used one, and then we tag those embedding vector by a popularity bits. And so when we're doing the replacement, we will avoid evicting the hot embedding vectors because they are frequently accessed, and we want them to stay in the cache as long as possible. And we access the L3 in batch, so that because keep in mind that L3 is in the SSD, although it's internal DRAM in the SSD. So we want to have more query or access to the L3 so that it can be scheduled properly to fully utilize the bandwidth of the internal bandwidth of the SSD devices. And then for the L3 cache, we give a flexible replacement granularity, because although the access granularity of the SSD is at a page level, but we can have a finer grain because we can actually fetch a page and only use part of it. And it is all happen internally at the SSD because L3 is located inside the SSD. So a flexible replacement granularity will guarantee us to select the best replacement granularity based on the workload, and give us the best cache hit rates on the L3 cache. And we also incorporate a prefetching policy that we replace a cache block with multiple correlated embedding vector, rather only replace the one with the vector that we require for this inference. So for this prefetching mechanism, at the outline, we first calculate all the popular or hot embedding vectors, as I mentioned before. And for all these embedding vectors, we calculate the correlation between them, which means if I access this vector, which actor will have the most possibility or have the highest probability that I will access in the following queries. So we will generate a swarm matrix according to these calculations, and we find the most possible pairs of those access, and give a correlation dictionary that's for for use during our prefetch of the L2 cache. So we also define a parameter called W, which is the window size of the correlated embedding vectors, because we hope that for the prefetch, we hope those access the vector could be stay within the same cache block or adjacent cache blocks, so that they can be grouped together and reduce the number of blocks that we need to replace during the prefetch. So we define a window size and only check the correlation if those the access of those two embedding vectors are within this window. And lastly, we also have a inference kernel that fully utilize the parallelism of those executions. So we have 3 levels of parallelism. So first is the inter-level parallelism, because we have multiple tables for the embedding lookup process, and we can calculate all these tables together. And the second is the intra-table parallelism, that the element-wise summation of multiple embedding vectors can be performed together using this tree, using this tree-like structure. And finally, we have the inter-vector parallelism, which we can use a vector adder to calculate the element-wise sum altogether during this calculation. So we also show this memory layout on the on-chip memory, so that we want to maximize those parallelism when we read the embedding vector outside of this on-chip memory. And this is our evaluation frameworks. So we have two parts. The outline parts show study the replacement granularity for L3 cache and the popularity analysis of the embedding vectors. So this is all done in software and do some statistical analysis of our workload. And the online part, we integrated simple SSD and emulator to the Geom5 and build the overall memory and simulate the overall memory system with the queries that we get from the dataset. So for the workload and baseline, we compare with the existing near memory and near storage solution for recommendation system inference. And we select 2 synthetic workloads from DeepRexSys and 2 real-world workloads that is used in the actual system. So this is the evaluation result. We can see that we can achieve up to 10.9 times speed up over the existing near storage solution, because we add an extra layer of cache, and this is very effective in reduce the access latency. And although in performance-wise, we may not outperform the near memory solution, but we are seeing like 6.6 improvement on the performance per dollar over the near memory solution, because the DRAM is actually much more expensive comparing with the SSD. And we also see a 72% of energy saving comparing to the near memory solution, because also the power consumption of the memory is much higher than the SSD. And we also see energy savings comparing with the near storage solution, because we showing like about 10 times performance improvement, although the SSD shows lower power. So we reduce the overall latency, but that we reduce the overall energy consumption. And then the cache design, we show over 83% of cache gate read over our data sets, because we have large L2 cache and we have the customized cache replacement policy. And we also show the effectiveness of the prefetching policy that increase the cache hit rate. And lastly, we performed an ablation study that's showing the effectiveness of these popularity bits. We show 1.27 times speed up, and because those popular embedding vectors frequently accessed will stay in the L2 cache longer, and comparing those ones that are already evicted. And we also show that the specialized inference kernel will improve the performance by 1.3, because the ERAM cascade size is set to 1, so that we have the maximum bandwidth of the on-chip memory. We also show breakdown of the inference latency. We can see that in our system, there's a 60% of time is consumed on the SSD and HBM access. So in conclusion, we propose a memory system design called EMSI with a specialized caching mechanism for recommendation model inference. It utilizes the CXL interconnect to construct a memory hierarchy of SSD, HBM, and on-chip memory on FPGA. The cache policy is workload aware and aims to minimizing the data movement overhead. We also include a inference kernel that supports the multi-level of parallelism. The evaluation shows we can achieve up to 10.9 times speed up over the SMC-based solution and 72% of energy savings compared to a near memory solution. And thank you. I'm open to any questions.
Thank you for the nice presentation. Any questions from the audience?
So, if I understood right, you are using DRAM as a cache, right? And
Could you repeat?
you are using DRAM as a cache,
Yes.
yeah, and you are prefetching from SSD large blocks, which will be of page size 4 KB.
We actually prefetching. So the L3 cache is the internal DRAM in the SSD, and we perform prefetching at the L2 level, which we
Okay.
prefetch from L3 to
So
the
you will be always accessing 4 KB pages from SSD
yes.
to the local DRAM. And doesn't it discourage the whole idea of using CXL based systems? Because these are the cache coherent interconnect systems.
Yes. I think here using CXL is that we want to so from L2 to L3 and actually we want to like minimize the data movement overhead. So if we are not using CXL, you have to read those data from SSD, either it's in the DRAM or in the NAND block. You have to read them to the main memory and
Like
then
with
copy that through.
Okay, yeah, like with CXL, we can also access blocks of caches on a small cache, means like 64 byte block.
This is actually like this is not like the cache in the
Yeah,
CXL.
yeah.
It is actually memory, so
So-
we use memory as a cache.
Okay, thank you.
Any questions? So I just have one question. So how did you, what kind of data set did you use to model the popularity distribution in the ZIF? You were mentioning you have ZIF popularity distribution, right? Log normal distribution.
Yeah.
So how did you model that? Did you use some data set for?
Yes. So we show this is so typically for the recommendation model, we will have the data set to train that. So we can sample part of the data from this data set to get all the statistical data. So yeah, I think this is a common practice on other recommendation systems.
Thank you.
Thank
There
you.
are no questions, then we will move with the next presentation. So the next presentation would be done through a video presentation. The authors are available on Zoom. It's not available. Okay, fine. So then they have sent a pre-recorded video.
Hello, everyone. I'm Zhi Bingsha from Southwest University of China. Today, I will present our work, which is about proactive stripe reconstruction to improve cache use efficiency of SSD-based RAID systems. This presentation has 4 parts. The first part is introduction. Thanks to advances in high performance, increases the capacity and lower power consumption, solid-state drivers based on NAND flash are widely deployed in embedded devices, personal computers, and data centers. Specifically, the widespread adoption of ternary number cell and ground number cell has decreased the per unit cost of SSDs, making SSDs dominant storage device. However, high-density NAND flash cells have a higher bit error rate and error checking and correction capacity of SSD is limited. Therefore, RAID is used to protect data in SSD. In RAID systems, a parity chunk is generated by all data chunks in the same strip, which is used to protect data chunks. As the example, the parity chunk P0012 can be computed by XORing operation on data chunks of D00, D1, and D2. Once a data chunk becomes inaccessible, RAID can recover the inaccessible data chunk. For example, by XOR checking data chunks D1, D2, and parity chunk P0012 belonging to the same strip, RAID recovered the inaccessible data chunk D00. The RAID systems, however, suffer a survival-wide penalty, which means that when data chunks are updated, the corresponding parity chunk must also be updated. For instance, when data chunk D00 is updated, the parity chunk P0012 must also be updated. The updated parity chunk and data chunk must be written back to old SSD location. This is done to ensure the effectiveness of RAID system. More importantly, we suggest that updating any data chunks must trigger an update operation on the parity chunk of the strip. Leading to the parity chunks are the most frequently updated. The frequently parity chunks updating has a significant negative impact on I/O performance, and it also increases the frequency of garbage collection, which shortens the lifespan of SSDs. To better boost the performance of RAID systems, it commonly employs a parity cache to absorb parity updates in SSD-based RAID systems. To avoid flashing the parity chunk to the NAND flash array. When a data chunk is updated, the parity chunk in the same strip will be recalculated and temporarily stored in the parity cache, such as the cache hold parity chunk P0012 and P345. The least recently used algorithm is the most commonly used method for managing the parity cache. It moves the parity chunk to the head of the linked list when the parity chunk in the cache is accessed, indicating the least recently accessed parity chunk is located at the tail of the linked list. We emphasize that each parity chunk corresponds to multiple data chunks in the same strip, and it does not indicate all data chunks associated with the frequently updated parity chunk are hot updated. In other words, the LRU for parity cache management may result in lower cache utilization efficiency. So, we proposed proactive strip reconstruction to improve cache use efficiency. This is a high-level overview of our proposal. Our basic idea is perform proactive strip reconstruction for shuffling data strips, which means the data chunks in the rebuilt strips may have similarly update hotness. Consequently, a proposed approach can result the cached parity chunks corresponding to hotter update data chunks and thus boost cache use efficiency. For example, two reconstruction candidate strips of strip 0 and strip 1 are matched as reconstruction pair. By referring to the update hotness of data chunks in both strips, we reconstructed data chunk of D0, D2, and D4 as the new data stripe of stripe 0. Meanwhile, the data chunks of D1, D3, and D5 are reconstructed as other new stripe of stripe 1. The parity chunk of new stripe 0 is kept in the cache, but parity chunk of new stripe 1 is flashed onto the underlying NAND flash array, and its data chunks are code update. There are two issues with respect to a proposal method of proactive stripe reconstruction, including which stripes can be classified as candidate for stripe reconstruction, and how to match two stripes for accompanying process of stripe reconstruction. We'll discuss these two issues. We propose comparing the access distance of a given stripe with the different threshold to determine whether the given stripe can be treated as reconstruction candidate or not. We first define the access difference as the difference in order between two adjacent data chunks in the same stripe. For example, the access difference of stripe 0 is 20 and 1. The access distance is maximal access difference. In the figure, the access distance of stripe 0 is 20. Because the access distance is larger than the threshold, so that this stripe can be classified as reconstruction candidate. Furthermore, we regard data chunks of D1 as cold data chunk that can be restriped with cold data chunks in the matched reconstruction candidate stripe. For example, data chunk 3 and data chunk 5 in stripe 1. Our approach aims to reconstruct to match the candidate stripe, and the primary matching principle is that the same type of data chunks in both candidate stripes must be distributed on the different read components without any overlap. Specifically, we employ two bitmaps to represent the SSD locations of old and closed data chunks regarding in the given data stripe, and it can detect whether there is a conflict or not. Note that 1 indicates the location of old or closed data chunk in the stripe. The parity chunk of reconstructed stripe corresponding to SSD 0 to SSD A3 and the match conflict. First, it performs and operation on the same type bitmaps of two candidate stripes to respectively get the conflict bitmaps of old and closed data chunks. After that, it can confirm two candidate stripes are matched or not by carrying out an OR operation on two conflict bitmaps. At least, if there are no conflict, we conducted an XNOR operation on the bitmaps of closed data chunks of two stripes to get the parity chunk location of the reconstructed code stripes. The figure shows 4 matching types of two candidate stripes, according to the location of old and closed data chunks in the involved two candidate stripes, as well as the location of parity chunk of reconstructed stripes. The type 1 match indicates a perfect match between two candidate stripes, and we do not perform other 3 match types. Once a match fails, we attempt to use prediction to eliminate conflicts. In Figure 1, we redirected write request from SSD 3 to SSD 1. It balances I/O workloads. Similarly, redirection emulates reconstruction conflicts in Figure B. In order to variety proposal method, we use SSD SIM to run real workloads. We implement our proposal in the SSD SIM. In the tests, we simulate 16.4 GB SSD. In the paper, the read buffer is set as 32 MB, 16.4 MB, and 128 MB to show the results in different buffer size. In addition, 8-block workloads are used to evaluate the proposal method, and the detailed information is shown in the table. There are 5 evaluated methods: baseline, PPC, patch, camp, and proactive. The baseline buffers parity chunks in the cache to reduce the number of parity chunk updates. PPC uses partial parity chunks produced by XORing updated data chunks within a stripe to replace parity chunks in the cache. Patch buffers only the modified parts of data chunk instead of the one chunk in the DRAM cache, so that it can absorb more updates on data chunks in the limited size of DRAM cache. Camp aims to unify access frequency of data chunks in the same stripe. By restoring to stripe reconstruction, it first analyzes recent history access to mine in the frequent sequence by using frequent sequence mining algorithm. Then it reconstructed new stripes by combining the data chunks corresponding to the frequent sequence. We agree the camp is the most related work. Proactive is our proposal stripe reconstruction method. The primary goal of parity cache management is to increase the number of hit on parity chunks in the cache, indicating these parity chunks are fresh to onto underlying SSD device. Thus, the number of cache hits is used as an indicator of cache use efficiency, where large number implies higher efficiency. In the figure, the y-axis is the increased hit compare baseline, and x-axis is different workloads. It is clear that proactive performance the best, and can increase the cache hits on parity chunks by an average of 6,056.6 or percentage of 2.3 on average. To further explore the reason for the implement cases by proactive, we also record the number of stripe reconstructions, and soon proactive triggers an average of 2,419.33 stripe reconstruction. The overall I/O response time is important indicator. Proactive can reduce the I/O response time by percentage of 12.2. Finally, let me make a brief conclusion on this work. We propose a method of proactive stripe reconstruction to improve parity cache use efficiency. in SSD-based read systems. We built a mathematical model to identify the stripes that consisted of both old and cold updated data chunks, and treat them as reconstruction candidates. Experimental result illustrate cache head radio can be increased by percentage of 2.3 on average. Our response time can be reduced by percentage of 12.2 on average. Thanks.
It's not there. No. Okay. So we don't have the authors on Zoom, so there is no question and answers then. The paper, the short paper, it will be presented by Dr. Lokesh Sittu. Dr. Lokesh is from Karlsruhe Institute of Technology and is a postdoctoral research at the Karlsruhe Institute of Technology, Germany. He received his PhD from the IIT Delhi. He has worked in Intel for 3.5 years before PhD. He has also got Best Paper nomination in 2022. His research interests are in the embedded systems, energy efficient computing. Here the paper is titled CNN, Leveraging PC Memory's Fast Write Mode to Accelerate CNNs. Over to you, Dr. Lee.
Thank you for the generous introduction. Hello, I'm Lokesh. I'm a postdoc at KIT. I'm working with Professor Jörg Henkel. This work is a collaboration between TU Dortmund and KIT. So in this presentation, we will discuss how to leverage PCM memory's fast write mode to accelerate CNN. Okay. So as we know, PCM is a popular non-volatile memory. It is suitable for adoption as a main memory, but one of the main challenges for PCM memories is the write performance. So interestingly, the PCM memory provides multiple write modes, and each of these write modes come with a trade-off of retention time. So to explain further, we might have a fast write mode in PCM, which provides lower write latency, but it also comes with a lower retention time. So in phase change memories, similar to DRAMs, they also drift, their resistance drifts. In DRAMs, we have capacitance, in which charge leaks. In phase change memories, we might have resistance as the element, and that drifts away. So we could have lower retention time, and to restore from retention time failures, we might need to refresh the data. So to explain this more quantitatively, we might have fast write modes with 550 nanosecond latency to 1150 nanosecond slow write mode, and the retention time can vary from 2 seconds to 3000 plus seconds. So with this introduction, many prior works have tried to actually use these fast write modes to improve performance. For example, in PC 2019, we had a policy called quick and dirty, and what it tries to do is when the memory is busy, they use fast write modes and reduce the average memory access latency. And when the memory becomes idle or relatively idle, then refresh is issued. So, so such a policy overall does improve performance, but it has two limitations. One of the major limitations is that the writes that happen in the busy phase are repeated in the idle phase. So writes become duplicated. And the other thing is this rewriting could extend even to the busy phases, which might cause stalling of the application. So we try to figure out, we try to see if we are aware of the retention time requirement, can we do something better than this? So for example, let's say this is the variable A. Let's say we know that it is quickly read after writing. So the retention time requirement for it is not too much.
So in such a case, if we are aware that the retention time requirement is not too much, we can use fast writes out here. Now, let's say we are given a similar information for variable B, and for variable C, we know that it has a medium retention time requirement, so we can use a medium write. And let's say variable D is read after a very long time after writing, so it has a higher retention time requirement, and we use the slow write there. So if we are aware of the retention time, we can actually avoid all the rewriting and refresh overheads. So there are two key questions. One of them is, how do we figure out, one thing is, if we know the retention time requirement, how do we indicate it to the runtime system? So we can add a fast write instruction for such variables. The other thing is, how do we figure out the retention time of a variable? In embedded systems, we can use profiling for specific applications to figure out the retention time. Just as a case study, if you look at neural networks, they have a data independent access pattern. So with varying, let's say, a CNN takes multiple images, whatever happens, but the access pattern that is there is data independent, and therefore design time profiling of the retention time could work quite well. So just as an example, for example, in inference, we have each layer generates an output which is consumed by the next layer. So intermediate outputs have a low retention time requirement, which can potentially use fast write. Even in training, we can use fast and slow write modes. In training, we have a forward pass, and output generated during the forward pass are used during the back propagation to calculate the weights. So in such a scenario, weights for the output layers are calculated first, and weights for the input layers are calculated at the last. And therefore, the forward path outputs we can have lower retention time near the output layers, and for the layers which are nearer to the input, they might require a higher retention time and could use slow write. In training, as we see, the retention time varies across the layers. Therefore, if we have multiple write modes, it could be beneficial. So I'll quickly move to evaluation. So we use a Gem5 NVMain based setup to evaluate the policy. We see about 22% lower execution time and 5% lower memory energy for the Swift CNN policy, which was described in the previous slide. So we have two variants of the policy: Swift CNN2, which is a simple variant of the proposed policy, which uses only 2 write modes, and we have Swift CNN3, which uses fast, medium, and slow, all the write modes, and has better performance. The results in this slide are normalized to an idealistic policy. When I say an idealistic policy, it only uses fast writes, does not do refreshes, and possibly gives an upper bound on the percentage performance benefit that we can get. So since in inference, mostly all the writes are fast writes, therefore we are able to actually achieve near the idealistic policy. I'll quickly go through the results for training as well. So in training, as we discussed in the previous slides, that we have retention time varying across the outputs. So we show the execution time behavior for the forward path outputs, then the backward propagation, and the weight update. As we discussed, that the layers nearer the output, they require lower retention time, and they might use fast writes. And for layers nearer the output, you will see that we get more gains as compared to the state of the art. Also, if you see carefully, the Swift CNN3 has more performance benefit as compared to the training case, as compared to the inference case out here, because of utilizing the medium write mode. So possibly we could discuss more on our poster. If you have more questions, I'll be happy to address at the poster. Thank you so much.
Thank you, Dr. Lokesh. We have time for one question. Do you have any question from the audience?
Yeah, thank you for the presentation. I think the PCM have some problem like endurance, the left time. So the left time of the slow rise and the fast rise is different or the same.
Could you repeat your question until I missed?
The endurance of the PCM, the left time of it. If the left time between the slow rise and the fast rise are same or different?
Yeah, I got your question. So actually there is some research which shows that slow rides harm the endurance more as compared to fast rides. That is one. Also, although you didn't ask, but as a future work, what we are also seeing is if you look at the state of the art policy, it first issues fast rides and then issues slow rides. So such a policy actually harms endurance as well. And we are trying to simulate in our evaluation, also include endurance in our future evaluations. We would be doing better because as it is, we are avoiding these extra slow rides, but slow rides affect the endurance in a worse manner as compared to fast rides.
Okay, thank you. Yeah.
Hey, this is a very good work, good presentation. I'm wondering if this technique can be applied to other emerging memories, for example, instant memory or like that for the lecture. Do you think?
Which memory is this?
Maybe RAM register.
Yes. So we have currently evaluated for phase change memory because somehow parameters were available more easily. But other non-volatile memories also could benefit from this. STT RAM I saw has also in one of the papers reported that there are multiple write modes available for it. And other memory technologies, non-volatile memory technologies, wherever there is MLC, I see there is scope of using this.
Okay, thank you. Thank you, Dr. Lokesh. We'll move ahead with the next presentation, the last session. It's again a short paper. It's titled No Multiplication Deterministic Hyperdimensional Encoding for Resource Constrained Devices. You have Nehra. The authors are available on Zoom. So we'll play their presentation first and then we'll go ahead with question and answers.
Hello and welcome. In this video abstract, I am going to provide a brief overview of our research on hyperdimensional computing, abbreviated as HDC. HDC is a revolutionary paradigm inspired by the structures of the human brain. Renowned for its attributes of lightweight design, robustness, error tolerance, and hardware efficiency, HDC has gained recognition for its applicability in image classification tasks. The HDC platform encompasses several basic steps, namely encoding, training, and inference. The encoding process involves generating hypervectors in binary shape and subjecting them to operations such as binding, bundling, and permutation, which respectively accounted as multiplication, accumulation, and shifting. To address the constraints posed by resource-limited devices, we have explored the utilization of quasi-random and deterministic sequences, aiming to reduce the model's complexity and increase hardware efficiency. The existing HDC models, known as based on HDC, employ two types of hypervectors to convey information about the intensity and positions of underlying images. Intensity hypervectors exhibit correlation for close values and uncorrelation for distant ones, while the position hypervectors are crafted through pseudo-random techniques to ensure orthogonality, signifying their dissimilarity. However, these prevailing HTC designs suffer from limitations in hardware friendliness and accuracy. To overcome these challenges, our research delves into the encoding phase of the HTC system, where we propose eliminating the need for position hypervectors. This is achieved through the integration of deterministic sequences, such as the Sobol sequence, generated orthogonal hypervectors. By comparing each pixel value with the allocated deterministic sequence, we assign position information, removing the necessity for explicit position hypervectors. Through this innovative approach, we eliminate the position hypervectors and the related multiplication procedure, resulting in a streamlined model that closely resembles baseline HTC in the remaining steps, but with a mitigated hardware cost. The key advantage of our proposed method lies in its ability to enhance accuracy while simultaneously reducing runtime and memory usage, facilitated by the utilization of deterministic sequences. Thank you very much for paying attention and reading our paper.
Is there? Oh, yeah. Yeah, Dr. Sarkar, are you there?
Yes, I'm here.
Yeah, okay. Yeah, thanks for the short presentation. So, are there any questions from the audience? Yeah.
Hey, Sarkar, very good work. What I'm wondering is that your the way you have mapped HDC, where is this benefit coming from? What operation is critical and which one you are optimizing?
As far as I hear correctly, you're asking the idea behind mapping the images into binary sequences.
Yes.
Yeah, this is actually under the main title of emergent computing, and we represent data in unconventional way with long bit streams. Thereby, we become robust to bit flips because each bit position is insignificant, so we don't encode using some binary 2 radix, and it's soft error robust to the bit flips. First advantage is this. Also, when we encode scalar data of images using their position and level hypervectors in, again, binary single LSP-based representation, then we reduce arithmetic operations such as multiplication, addition, just into the single level logic gates such as XORs, population counters. Thereby, while we are training our model, we don't use conventional multipliers and adders. Instead, we just use the logic operators. And it's also the single pass training. With this mapping, we obtain these advantages actually.
Did you measure the improvement in energy efficiency or performance? Talked about resilience.
You mean the soft errors and the robustness of this representation?
Yeah, no, I'm talking about any improvement in energy efficiency. Did you calculate that?
For this work, we didn't target the energy efficiency actually, because this kind of emergent computing is always have a kind of trade-off for energy efficiency due to the long latency. But for the power, yes, we can say area power delay product is improving always. But for energy is always a challenge actually, because of you propose to represent the long bit streams. There are some works also targeting energy efficiency, but not in our scope for this work, but we are currently working on it. But for this work, we are more on the robustness side and the power efficiency side.
Thank you.
I thank you for your questions.
So I have one question. So you were mentioning about the immersive computing, right? So are there any applications that you are targeting for this kind of work?
From the application side, we are first working on the well-known data sets such as MNIST, MNIST Fashion, CIFAR. In addition to image processing, we are also working on, like other research groups, the language processing. But also, we are these days trying to increase the applications such as segmentation. For example, there are very few works making some image segmentation by using this processing environment. So next, our research agenda is including some a little sophisticated image processing tasks, such as segmentation and more.